Imagine staring at the edge of the universe. What do you think you'd see? A wall? A glowing barrier? Or absolutely nothing? In this Science for Sleeping video, you'll discover how scientists think about the edges of space and why those edges might not exist at all. Get ready to challenge everything you thought you knew about the cosmos. What exactly is space? Space often feels like the ultimate nothing. It's that deep, black backdrop we see when we look up at the stars, the vast emptiness stretching between planets, stars, and galaxies. It's easy to imagine it as completely still, a silent void where nothing ever happens. But stick with me for a moment, because that's not exactly true. In fact, even in the emptiest regions of space, there's an astonishing amount of activity happening, just not the kind we're used to seeing. Let's start with how space is often described. People tend to think of it as a vacuum, the kind of place where sound can't travel because there's no air. And sure, if you were to go out into space without a suit, you wouldn't find any oxygen molecules bouncing around. But to call space empty misses the bigger picture. At the tiniest scale, smaller than atoms, even smaller than subatomic particles, space is anything but quiet. It's buzzing with something scientists call quantum fluctuations. These are tiny, unpredictable movements of energy that pop in and out of existence, even in regions where we think there's nothing at all. So the void isn't truly void, it's surprisingly busy at a level we can't see with our eyes. One way to think about this is to imagine a perfectly still pond. To the human eye, it might look completely calm. But if you zoomed in close enough, way closer than even a microscope could take you, you'd see molecules of water moving, colliding, and vibrating constantly. Space works much the same way. Even in places far from galaxies or stars, where our telescopes can't pick up anything, there's an invisible pond of quantum fields rippling beneath the surface. And these ripples aren't just theoretical. They give rise to something known as vacuum energy. You may never have heard of this term, but vacuum energy is one of the reasons space can't truly be empty. Imagine a point in space where you've removed all the particles, light, and matter you possibly can. Even there, the energy from those quantum fluctuations still exists. It's not something we can see, but it's there, woven into the very fabric of space itself. Think of it this way. Space isn't just black nothingness. It's more like a trampoline that's constantly shifting even when nothing seems to be happening on its surface. And just like how a trampoline sags when you press down on it, space can stretch, warp, and twist based on the forces acting on it. But there's another layer to this, something that connects modern science to the very beginning. Let's go back roughly 13.8 billion years. When the universe was born in the event we call the Big Bang, it left behind traces of its origins that still linger today. One of those traces is heat, a faint glow spread out across space that we now see as the cosmic microwave background, or CMB for short. This glow isn't just a relic, it's proof that space has been filled with energy since the very beginning. Even in the coldest parts of the universe, this ancient warmth can be detected. We're talking about temperatures just a fraction of a degree above absolute zero. But it's still there, like cosmic leftovers that never got cleaned up. If you connect these pieces together, the quantum fluctuations, the vacuum energy, and a leftover warmth from the Big Bang, it becomes clear that space isn't empty at all. It's a dynamic, vibrant fabric, constantly shifting and responding to the forces around it. Even when it looks calm, there's this incredible undercurrent of activity woven into its nature. Now, why does this matter? Well, for one thing, it changes how we think about the universe itself. If space is more than just a blank canvas, then it's playing an active role in shaping everything we see. Galaxies, stars, and planets, All of it exists and moves within this energetic, shifting framework. The universe isn't just expanding into a static void. It's stretching something real, something rich with energy and history. And this realization didn't come overnight. For centuries, scientists assumed space was just an endless, unchanging emptiness. There wasn't much reason to think otherwise. It's not like you can see quantum fluctuations or vacuum energy by looking up at the sky. But as we've developed better tools and deeper theories, we've started to understand that space itself is far more complex than our eyes can tell us. In fact, thinking of space as a living, moving fabric opens up some important questions about its size and structure. Questions we'll dive into soon. If space can ripple and shift, what does that mean for its boundaries? Does it stop somewhere? Or does it stretch so far that it loops back in on itself like the surface of a sphere? These are the mysteries we face when we stop seeing space as just nothing and start recognizing it as a dynamic system full of energy and possibilities. So, as we go forward, try to hold this new idea in your mind. Space isn't just an infinite void. It's a constantly active fabric, infused with leftover energy from the birth of the universe and teeming with quantum activity that defies our intuition. Understanding this helps us ask even bigger questions like, if space is always stretching and changing, how far does it actually go? To answer that, we'll need to take a closer look at the people who first challenged the idea of space as static and introduced us to the idea of a universe in motion. How Einstein transformed space from static to stretchy. All right, let's talk about space, but not in the way you're used to. What if space isn't just some vast, unchanging stage where the universe plays out, but something alive? Not alive in the way you and I are, of course, but actively doing something, stretching, twisting, bending. It might sound strange, but this is exactly how we now understand space. Before that, though, the way scientists thought about it was much simpler. Let's rewind a few centuries to Isaac Newton. Newton's universe was clean and orderly, with space acting as the ultimate constant. If you could imagine it, he thought of space as a kind of invisible, perfectly still grid that stretched out forever. Stars, planets, and everything else moved through this giant grid, all obeying the predictable laws of motion that Newton himself helped define. It made sense for its time. After all, if you look up at the sky, nothing about space seems to move or react. It felt logical to think of it as an empty container, where everything just happens. But Newton's version of space had one critical flaw. It wasn't dynamic. It was a background, a place for objects to exist, but it didn't actually do anything itself. For centuries, this idea was accepted without much debate, because there wasn't much evidence to challenge it. Space just was. And then Albert Einstein came along. Einstein's big idea was that space and time weren't separate things at all, but instead parts of a single unified concept, space-time. This was groundbreaking because, in Einstein's view, space-time wasn't static. It could bend, stretch, warp, and even ripple like water disturbed by a pebble. And what caused all of this movement? Mass and energy. In other words, the very objects Newtonian physics saw as just floating through space were actually shaping the space around them. This can be hard to picture, but imagine a trampoline. When it's empty, the surface is flat, like Newton's fixed grid of space. Now, place a bowling ball in the center of that trampoline, and what happens? The fabric dips under the weight. If you roll a marble across the surface, it doesn't follow a straight path anymore. It curves toward the dip. This is similar to how massive objects like stars or planets distort space itself, bending the paths of smaller objects and even light. What's fascinating here is that gravity, which Newton thought was simply an invisible force pulling objects together, turns out to be something deeper, the result of space curving in response to mass. Einstein's idea transformed how we think about the universe. Suddenly, space wasn't just sitting there. It was active, a literal fabric that responded to what existed. There's something even more mind-bending here. Einstein's theory didn't just stop at this stretchy, curved space-time. It also showed that this process wasn't limited to individual objects like stars or planets. The universe itself was stretching. This idea, now called cosmic expansion, means that not only is space-time active, but it's growing larger over time. And here's the kicker. This stretching of space-time explains why galaxies appear to move away from us, with more distant ones receding faster. It's not that they're speeding off through space, it's that the space between us is expanding. It's like dots drawn on a balloon. When you blow it up, the dots get farther apart because the surface grows, not because the dots are moving across the surface. People didn't take Einstein's ideas lightly at first. For such a long time, science had clung to the view that space was rigid and absolute. A universe that could expand, let alone have the ability to warp and ripple, sounded far-fetched. But Einstein's equations kept holding up, and over time, they not only explained the phenomena we could already see, but also predicted new ones. One of the most fascinating examples of this is the way massive objects bend light. Think of a distant star. If there's something incredibly massive, like a galaxy cluster, sitting between us and that star, the light from the star doesn't travel in a straight line. Instead, it curves around the massive object because space-time itself is bent. Today, we see this phenomenon, called gravitational lensing, all the time in telescope images. It's one of the many ways Einstein's stretchy space-time theory matches the real universe. But there's one more important thing to consider. If space is like a stretchy fabric, then what does that mean for its whole structure? Is it infinite? Does it loop back on itself? Could it eventually tear? Well, before we dive into those mysteries, it's worth pausing to really appreciate how Einstein's ideas turned our understanding of the universe upside down. Space went from being a passive container to an active player, constantly shaped by everything within it. It's not static. It's not unchanging. Space, in many ways, shapes what we experience as reality. So now we have this image of space as a flexible, lively fabric. But just how far can it stretch? Is there a limit, or could it go on forever? Those are the questions we'll explore next. How big is the observable universe? The universe is 13.8 billion years old. That's a long time. Longer than our planet has existed. Longer than life as we know it. Longer than we can really wrap our heads around. But here's something that doesn't seem to add up. The observable universe. The part of the cosmos we can actually see. Let's start simple. The observable universe is exactly what it sounds like. The portion of the cosmos that we can observe. Everything within this region has emitted light, signals, or some form of radiation that had enough time to reach us, since the universe began with the Big Bang. The key word here is enough time. Light travels astonishingly fast, roughly 300,000 kilometers per second, but it's not instant. So, as we look out into the depths of the universe, we're really looking back in time. A galaxy a billion light-years away isn't just far. It's showing you what it looked like a billion years ago, when its light first began the long journey to get here. But that explanation might make the numbers even more baffling. If the universe has existed for 13.8 billion years, shouldn't we only be able to see about 13.8 billion light years away? You'd think so. But the cosmos has a twist. Space itself is stretching, and it's been stretching since the beginning. This expansion of space allows light to cover much greater distances than we'd intuitively expect. Imagine blowing up a balloon with tiny dots drawn on its surface. As the balloon stretches, the dots grow farther apart, not because they're moving across the surface, but because the surface itself is expanding. The same thing happens with space-time, enabling light to travel far beyond the simple limits implied by the age of the universe alone. That's where we get the jaw-dropping number, a diameter of 93 billion light-years for the observable universe. Light from the most distant edges of this bubble has been traveling for almost the entirety of the universe's lifespan. But because space has been expanding all the while, those regions are now far from where they were when the light first started moving. It's a bit like trying to measure how far the finish line of a race is when the track itself keeps getting longer while you run. At the heart of all this is something called the cosmic horizon. This isn't a solid boundary you could touch, or even reach for that matter. Instead, it represents a sort of limit, the farthest distance from which light or information can travel to us, given the universe's expanding age. Picture standing in a dense fog. You can't see past a certain point, not because there's nothing out there, but because your view is blocked by the conditions around you. The cosmic horizon is our version of that fog. What lies beyond it might very well exist, but whatever is out there hasn't had the time, or perhaps the opportunity, to reveal itself to us. And within this cosmic sphere, well, the numbers are staggering. Inside the observable universe, there are about 2 trillion galaxies. Each one contains millions, if not billions, of stars. The light we see from many of these galaxies embodies an almost unfathomable journey, crossing billions of years before hitting telescopes or your retina display in some cases. Some of that light started its trip before the Earth even formed, carrying with it ancient echoes of a universe that's constantly growing and evolving. What we're observing is more than just a cosmic snapshot. It's a time machine, showing us galaxies as they once were instead of what they are right now. And because we live in an expanding universe, this story gets even more surreal. There are galaxies so far away that they're moving away from us faster than the speed of light due to the ongoing stretching of space. That might sound like it breaks some fundamental rule. Nothing should travel faster than light, right? But here's the catch. It's not the galaxies themselves zooming off at impossible speeds. It's the space between us that's expanding, steadily increasing the distance in ways our intuition can't easily grasp. For these galaxies, the light they emit now will never reach us, no matter how long we wait. They're slipping out of our observable universe for good, vanishing into regions we'll never be able to see. Still, as vast as the observable universe is, it's just a fraction of what might actually be out there. That 93 billion light-year bubble isn't the whole story. It's just the part of the cosmos that's had time enough to communicate with us. A lot depends on how big the overall universe is. If it's infinite, then the observable part is nothing more than a tiny patch, like a single speck of sand in an unending desert. But even if the universe is finite, it's very likely that its total size is much larger than the region we can see. The expansion of space has sliced us off from the rest, leaving us with only this enormous but incomplete view. And even within the observable universe, light doesn't behave in the way you'd expect. As it travels through expanding space, the wavelengths of that light stretch out too, a process called redshift. Take a photon of light released by a distant galaxy billions of years ago. By the time it reaches us, that photon has stretched so much that its wavelength has shifted entirely, moving from visible light into infrared or microwave regions of the spectrum. This is how scientists are able to measure cosmic distances. They trace how much redshift has occurred, and in doing so, piece together the story of how fast space is expanding and how quickly galaxies are retreating from each other. There's more than one kind of cosmic horizon, though. The observable universe is one limit, carved by the speed of light and the universe's age. But there are other boundaries, like the event horizon, a limit beyond which events are forever cut off from us due to how fast galaxies are receding. Over time, the growing influence of an enigmatic force called dark energy means more and more parts of the universe are crossing that event horizon, permanently split off from anything we'll ever experience. It's a bittersweet reminder that the cosmos isn't just vast, it's also heartbreakingly out of reach in ways we're only beginning to understand. So, when we talk about the edge of the observable universe, we're not really talking about an edge at all. It's a window, an incredible 93 billion light-year wide perspective on the cosmos. But it's also just the tiniest sliver of the true universe. What lies beyond that horizon, we may never know firsthand. It could go on infinitely. It could loop back on itself. It could change in ways we can't imagine. What we do know, however, is that the observable universe doesn't contain all the answers. It's just the beginning of something far larger, far stranger, and far more mysterious than we're currently equipped to fully grasp. And so, we return to this idea of the universe as an ever-growing fabric, one that stretches out farther than we can see or imagine. If the observable bubble is just a small slice, how do we begin to understand what lies beyond? Could it go on forever? Or is there a chance, however small, that the total universe itself wraps back on itself, like a giant cosmic loop? These are the kinds of questions that aren't just fun to ask. They're fundamental to how we see our place in the cosmos. Let's continue to explore what might lie beyond the furthest limits of our sight. What lies beyond the observable universe? If the observable universe is just our slice of the cosmos, what's out there beyond it? This is one of those questions that starts off simple, almost childlike, but the more you think about it, the bigger and stranger it becomes. Everywhere you look, the cosmos seems to stretch endlessly, with no obvious edge, no sudden drop-off marking the end of existence. But remember, the part of the universe we can see is limited not by the vastness of the cosmos itself, but by the speed of light and the age of the universe. So while the observable universe is already staggering in size, 93 billion light-years wide, it's only a fraction of the full picture. To understand what's beyond that, we need to pause and acknowledge something important. We can only see so far because light takes time to reach us. Even as we peer into the deepest corners of the observable universe, we're only seeing objects whose light has had enough time, billions of years, to make the journey. Anything farther than that is effectively invisible to us, hidden behind what's called the cosmic horizon. It's not that nothing exists beyond that point, it's just that the information hasn't had enough time to arrive. The universe could extend far beyond what we can currently measure, but the reality is that we'll never get a direct look at what lies out there. The cosmic horizon is like an unbreakable barrier, locking us inside our own observable bubble. Think of it this way. If you stood on a distant galaxy 10 billion light-years away, your observable universe would overlap with ours, but it would also include regions of space we can't see and likely never will. Everyone, everywhere, has their own personal slice of the universe, shaped by their unique position in the cosmos and the limits of how far light has traveled. This makes the observable universe highly local, even though its size feels impossibly large. So, what's beyond our cosmic horizon? One possibility, and perhaps the most mind-boggling, is that the universe is infinite. If that's the case, it would mean the observable universe is just a speck in an unending expanse of space, like seeing one drop of water and knowing it's part of a limitless ocean. And an infinite universe comes with some wild implications. If space stretches on forever, then the amount of matter it contains might be infinite too. That's where things get strange. In an infinite cosmos, patterns will inevitably repeat. Eventually, if you go far enough, there would have to be not only stars and galaxies that look similar to ours, but arrangements of matter identical to what's here. Somewhere out there, there could be a duplicate Earth. Somewhere else, a version of you, or many versions of you, living slightly different lives, or even lives so similar to yours that the details match exactly. It's a bizarre idea, but it happens when infinity enters the equation. Endless space brings endless possibilities, including some that feel impossible. Of course, we should stop for a moment to acknowledge a key limitation here. We can't measure infinity. You can't map it or photograph it. As someone once said, we don't measure infinity the way we measure, say, the distance to the moon. You can't stick a ruler on space and keep going until the numbers run out. Infinity isn't a number. It's a concept, an idea that defies physical measurement. So while the idea of an infinite universe is a tantalizing one, it's not something we'll ever be able to confirm by direct observation, no matter how advanced our technology gets. Infinity isn't the only option, though. It's also possible that the universe beyond our observable bubble is vast, but finite. Imagine a gigantic room that extends so far you can't see its walls. Just because you can't see the edge doesn't mean it's not there. In the same way, the universe might stretch far, far beyond what we can directly observe, but eventually come to an end. What that end looks like is a whole other mystery. Does space just stop, like hitting a cosmic wall? Or does it fold back on itself, creating something more complex, like a finite but unbounded surface? Now, here's where things get really intriguing. Even if the universe is finite, it doesn't mean everything out there looks the way it does here. The regions beyond our observable horizon might be completely unfamiliar. Different kinds of matter, physics behaving in ways we can't imagine, even fundamental constants, like the speed of light or gravity, shifting to values unlike anything in our local universe. There's no guarantee that the rules we see here apply everywhere. We have some evidence to work with, though. When we look in every direction, we see no detectable edge. Everything seems smooth and uniform, which hints that this pattern might continue beyond the observable universe. But how far? That's where we run into philosophical, as much as scientific speculation. Infinity isn't just a measure of size, it's a shift in how we think. It changes the universe from something big into something boundless, something impossible to fully comprehend. The part of the universe we can see feels enormous, but in an infinite cosmos, it barely makes a dent. So, if the universe is infinite, or even just incredibly large beyond our reach, what does that mean for us here on Earth? In one sense, it's humbling. When you realize how tiny our observable bubble is compared to what might be out there, it puts our place in the cosmos into perspective. But there's also something strangely comforting about the vast unknown. Knowing that most of existence lies beyond what we'll ever see reminds us that we're part of something bigger, something so grand and mysterious that it transcends our ability to fully grasp it. We may never know for certain how the universe behaves beyond the cosmic horizon. It could stretch endlessly, continuing in its uniformity forever. Or it could loop back on itself, forming a strange, multidimensional structure that's fundamentally different from what we perceive. Either way, both options are equally fascinating. The universe might not have edges in the way we imagine, but it could still have a shape, a characteristic that gives it boundaries or structure even if those boundaries don't appear as walls or barriers. And this brings us to our next big question. If the universe is infinite, how do we reconcile that with the idea of space potentially wrapping back on itself? Does space have an overall shape? Could it be flat, curved, or something else entirely? Let's explore how geometry ties into the way our universe is structured, and what that structure might tell us about where it begins, where it ends, or whether it simply goes on forever. Does space have a shape? Could the universe have a shape? Maybe it's flat like an endless sheet of paper, curved like the surface of a balloon, or shaped in a way that's harder to wrap your head around, like a giant cosmic donut. Believe it or not, this isn't just a fun thought experiment. It's a real scientific question, and one that tells us a lot about how the universe works and what its limits might be. But before we get into the details, let's talk about what we mean when we say shape in this context. The shape of the universe isn't about having walls or edges. Instead, it's about geometry, the way space behaves as a whole. Is it flat and endless? Does it curve inward like a sphere or outward like a saddle? To figure that out, scientists look at how the geometry of space ties into something called the universe's density. This refers to how much matter and energy is packed into space compared to a value known as the critical density. This critical density acts like a balancing point, where even the tiniest difference can create big changes in how space behaves. It's sometimes called the Goldilocks of cosmology, because the universe's density has to be just right, not too much, not too little, to reach a specific shape. So what happens if the actual density doesn't match this critical value? If it's greater than the critical density, the universe curves inward, creating what's called a closed shape. Picture the surface of a sphere. If you travel far enough in one direction, eventually you'll loop back to your starting point. Parallel lines don't stay parallel forever. Instead, they eventually meet, like lines of longitude converging at the poles. Closed spaces like this are finite. They have a definite volume, but they don't have an edge. There's no point where you fall off or hit a hard stop. Now, if the density is below the critical value, space curves outward, creating an open shape. This is often compared to the surface of a saddle. Here, parallel lines don't meet, they actually drift farther and farther apart. An open universe keeps expanding forever, getting more stretched out and spread thinner over time. This type of geometry means space is infinite, without any looping or repeating patterns. And if the actual density matches the critical density perfectly, you have a flat universe. In this case, space doesn't curve at all. It stretches out evenly in every direction, like a piece of paper that keeps going forever. Think back to your early geometry lessons. In a flat space, parallel lines stay parallel no matter how far they're extended. If you draw a triangle and add up the angles, it'll always equal 180 degrees. A flat universe doesn't loop back on itself, but it doesn't curve outward either. It's just flat. But flat doesn't mean simple. Even a flat universe can be either infinite, going on forever, or finite, wrapping around in ways that are hard to visualize. Let's break this down with a few simple analogies. Imagine an ant trying to explore its world. On a flat sheet of paper, the ant can keep walking in a straight line forever without turning. This represents a flat universe. Now place the ant on the surface of a balloon. As it walks, it'll eventually make a full loop and end up where it started. That's a closed universe. Finally, place the ant on a saddle. No matter which direction the ant walks, the surface keeps curving away. This is an open universe, curving outward infinitely. To figure out which of these shapes matches reality, scientists turn to the oldest light in the cosmos, the cosmic microwave background, or CMB. This afterglow of the Big Bang holds tiny clues about the universe's geometry. By mapping the patterns of this faint light, specifically the tiny temperature fluctuations within it. Researchers can see whether space bends light over vast distances. These temperature variations act almost like a cosmic ruler. If the universe is flat, they appear a certain size. If it's curved, those patterns look either larger or smaller depending on the shape. And here's the surprise. All evidence so far suggests the universe is incredibly close to being flat. By studying this ancient light, scientists have found that any curvature, whether inward or outward, is so subtle it's currently beyond our ability to measure. Space may not be perfectly flat, but if it's bent on a mind-blowingly large scale. Picture being on Earth and trying to see if the horizon curves. Only now imagine doing it over distances millions of times larger than our observable universe. That said, a flat universe doesn't automatically mean one that goes on forever. This is where things get tricky. Even though we think of flat as something infinite by nature, there's another possibility. That space could be flat but finite, with no edges. The surface of a sphere provides a good example. If you were to walk along the surface of a globe, you'd never find an edge. But your journey would eventually loop back around. Now, take that concept and extend it to 3 dimensions. Space itself could curve back on itself in a way that we wouldn't notice from our perspective. Because we're inside this space, and because it's expanding, the curvature would be too subtle for us to perceive directly. So, could the universe really be shaped like a giant cosmic loop? It's possible. If space is finite but unbounded, it wouldn't need edges to keep its size contained. Instead, it would simply wrap around on itself, creating a kind of continuous environment where straight lines might eventually lead you back to your starting point. Some researchers have even proposed that we might be able to detect this looping shape by looking for repeating patterns in the cosmic microwave background, like seeing the same patch of universe from different directions. So far, though, no such patterns have been found. Here's the fascinating part. The shape of the universe is tied directly to its destiny. If the universe is closed, its expansion might eventually slow down, stop, and reverse in a big crunch, collapsing back in on itself. If it's open, it could expand forever, thinning out as galaxies drift farther apart. And if it's flat, that's a middle ground. The universe would expand forever too, but at a rate that slows just enough to avoid breaking the structure of space itself. In this sense, the geometry of space isn't just a question about its size or shape. It also affects the ultimate fate of everything within it. All of this underscores just how much we're still learning. While the evidence points strongly toward a flat universe, there's still so much about its shape and structure we don't fully understand. Is it truly infinite? Could it loop back on itself in subtle, unobservable ways? Or does it have some exotic geometry we haven't even imagined yet? The answers to these questions will shape not just our understanding of space, but the nature of reality itself. Which brings us to a striking possibility. If space can loop in a way that's finite but unbounded, what about traveling through it? Could you set off in one direction, travel forever, and eventually end up back where you started? It's a strange idea, but one that opens the door to even more questions about how space behaves on the grandest scales. Let's explore that next. Could you travel in a straight line and end up where you started? What if, instead of traveling across the universe on a seemingly endless journey, you could fly straight in one direction, forever, and eventually end up back where you started? No edges, no barriers, just one continuous path that loops back on itself. It might sound like science fiction, but in cosmology, this idea is tied to how space itself could work. A universe without boundaries, yet finite in size, is one of the fascinating possibilities when we think about the shape and structure of space. Let's break it down. To picture a finite but unbounded universe, it helps to imagine a simpler two-dimensional example. Take the surface of a sphere, like a globe. If you're an ant walking on that surface, you'd find that you can go in any direction indefinitely, but eventually you'd end up right back where you began. There's no edge to fall off from, no wall to stop you. And yet your journey is still contained within the limits of the sphere's surface. In 3 dimensions, space could theoretically work the same way, curving back on itself so that traveling in a straight line long enough might bring you full circle. So what does this mean for the universe we live in? One way to think about it is with the balloon analogy. Imagine the surface of a balloon as representing all of space. Galaxies are like tiny dots drawn onto the balloon's surface. As the balloon inflates, the dots move farther apart from each other, not because they're crawling across the surface, but because the surface itself is expanding. Now picture this on a cosmic scale. Space itself stretches and grows, carrying galaxies along with it. If that surface loops back on itself like the sphere, you could theoretically set off in one direction and eventually return to your starting location, just like our hypothetical ant. Here's the tricky part, though. In this analogy, our universe's surface isn't something we stand on or observe from the outside. We're inside it. The 3-dimensional nature of space adds a layer of complexity. Our universe might curve through a higher dimension in ways we simply can't detect from our vantage point within space. Think of the ant on its balloon. The creature can go around the surface, but it can't perceive the balloon's curvature into 3-dimensional space. Similarly, we might not perceive how space curves if it warps in a way we could only observe from outside the universe, and that's not something we're able to do. The idea of an unbounded universe, where a straight path could loop back, sounds simple enough, but proving it? That's where the challenge lies. Researchers have looked for evidence of this by mapping the cosmic microwave background, CMB, the faint afterglow of the Big Bang.
If space loops back on itself, any light or radiation that's traveled the full circle of the universe might create duplicate patterns within this ancient cosmic light.
For example, you might see the same cluster of galaxies appear in multiple locations across the sky, like reflections in a funhouse mirror. But so far, scientists haven't found these telltale repeated patterns, or at least not with absolute certainty. The absence of evidence doesn't rule it out. It just means the universe might be so large that any repeating features are too subtle or far away for us to detect. It's here that another analogy might help. Think of video game maps from older arcade games like Pac-Man. On some levels, if you move your character off the left side of the screen, it pops back onto the right side, like the edges loop around and connect invisibly. There aren't real walls stopping Pac-Man from moving. The space just naturally wraps in that way. This is a 2-dimensional example of a concept called a toroidal universe, shaped like a donut. In 3 dimensions, a toroidal universe would mean space connects in a similar way, looping back on itself. Theoretically, you'd never find a boundary. You'd just keep moving, always coming back to where you began. While this doesn't guarantee our universe is shaped like a giant cosmic donut, it's one way to illustrate how space could be finite but give the illusion of being endless. But that brings up another question. How do we prove for sure whether space is open, flat, or curved? It comes back to what we talked about earlier, the density of the universe. How much matter and energy are packed into space determines whether the universe curves inward, outward, or remains flat. And while all evidence so far suggests that our universe is very close to flat, that doesn't completely eliminate the possibility of some curvature on unimaginable scales. If space does have some curvature, then its ability to loop back on itself becomes a real possibility. Even still, there's another challenge to consider. As the universe expands, the galaxies farthest from us are moving away faster and faster due to the stretching of space itself. Over time, this might mean that objects on the other side of a looped universe become unreachable because that space is expanding too quickly. Imagine trying to walk across that balloon's surface while it's growing larger with every step you take. You'd still loop eventually, but it might take infinitely longer to complete the journey as the surface expands. Practically speaking, this would prevent us from ever observing or experiencing the supposed looping nature. If all of this seems a little abstract, that's because it is. Much of this discussion exists in the realm of theoretical physics, where we rely on models and analogies to describe things that are hard or even impossible to visualize. Space isn't like anything we encounter in daily life. It's not a physical object, but a framework, one that doesn't need an outside or an edge to make sense. Earlier, we imagined the balloon expanding in the air, but space isn't sitting inside something larger. It is the thing. There's no external void beyond it, no bigger balloon holding it. That's a very human way of trying to understand boundaries, one that doesn't apply at the scale of the universe itself. Still, the possibility of curved looping space leads to a strange realization, that space doesn't need edges to create limits. Instead, its structure, how it folds, stretches, and connects, determines whether it's infinite or bound. The absence of a boundary doesn't mean endless freedom. It might mean that the universe simply rounds out wherever you are. Now, here's where things get even more fascinating. Whether the universe loops back or stretches infinitely, either option blows open the doors of what's possible. A finite, looping universe might limit where you can go, but it also raises questions about how space cycles energy, matter, or even time itself. An infinite universe, on the other hand, introduces possibilities so bizarre that they challenge our very understanding of uniqueness and identity, ideas we'll dive into next. So, while space may not have sharp edges or hard stops, it might behave in ways that reshape how we think about motion, distance, and the very fabric of reality itself. Whether or not you could ever complete a cosmic round trip is almost beside the point. The beauty here lies in contemplating a universe so strange and so different from our everyday experience, yet so fundamental to the existence of everything. The strange consequences of an infinite universe. If the universe truly is infinite, the possibilities that come with it are both dizzying and deeply strange. You might feel like infinity is just a fancy way of saying really big, but it's not. Infinity is its own kind of concept, a boundless expanse where even the most improbable events don't just happen once, but must happen over and over again, simply because there's infinite room for them to exist. And this means something pretty wild. Out there, somewhere in the farthest reaches of an endless cosmos, there could be an exact copy of you. Or at least, someone, or something, almost exactly like you. Let's start with what infinity fundamentally implies. If space stretches on forever, then the laws of probability start working in a way that feels almost like magic. Picture flipping a coin. If you flip it enough times, you'll eventually see every possible outcome of heads and tails show up in every possible sequence. Now extend this idea to the universe. With an infinite amount of space, there's an infinite number of ways matter can combine, but there's also an inevitability that those combinations will repeat. Somewhere far, far away, the same arrangement of atoms that make up Earth could assemble again, replicating a world eerily similar to ours. And it doesn't stop with planets or solar systems. If the universe is infinite, it's reasonable to wonder if there's not just one version of you, but countless versions. Somewhere out there could be a closer than identical copy of you, living a life almost identical to yours, but with tiny differences. A different choice made over breakfast, or an outfit a shade lighter than the one you chose today. The sheer scale of infinity erases any idea of uniqueness as we know it. The laws of probability demand that if you wait long enough and search far enough, everything will eventually happen again, just slightly, or even exactly, the same. It's a thought experiment that feels almost too much to comprehend, but it actually has roots in real science. Many of these ideas are tied to what physicists call the cosmological principle. This principle states that the universe, on the largest scale, is both homogeneous and isotropic. In simpler terms, matter is spread out evenly, and the physical laws work the same everywhere. If this holds true into the infinite stretches of space, the implications are profound. The observable universe, that 93 billion light-year bubble we mentioned earlier, would just be one patch in an endless quilt of other regions. And in that endless quilt, the same patterns must show up again and again. Here's an easier way to think about it. Imagine you're holding a deck of cards. There are only so many ways to shuffle that deck. 52 cards can only be rearranged in a finite number of combinations. But now imagine you're playing with an infinite number of decks. Sooner or later, you'd encounter a shuffled order that's identical to one you've seen before. In the same way, an infinite universe means an infinite deck of possible arrangements of atoms, stars, galaxies, and planets. There's nothing stopping some of them from ending up as exact or near-exact duplicates.
And this idea leads us to something even more mind-bending. Alternate versions of reality. If the universe is infinite, and if patterns repeat, there may be regions of space so far removed from our own observable patch that they might as well be separate universes entirely. These aren't the parallel universes of science fiction, generated by splitting timelines or alternate dimensions. These are duplicates that exist in the same physical universe as ours, just unimaginably distant. The light from those other versions of Earth and you will never reach us because of the cosmic horizon. They're separated from us not by a wall or barrier, but by sheer vastness and the reality of space itself. To make infinity feel a little more tangible, let's bring it down to Earth for a moment. Imagine standing in a mirrored hallway that stretches out to infinity. At first, the reflections seem unique, some turned at different angles, some slightly dimmer, but as you look deeper, you notice the same patterns repeated again and again. You're seeing yourself reflected endlessly, creating an illusion of copies that fade into eternity. An infinite universe works similarly, except instead of mirrors reflecting a limited space, it's real matter repeating itself across vast, infinite distances. But there's something even stranger about all this. If patterns repeat across an infinite universe, it raises questions about the very nature of identity. What makes you unique if there are likely multiple versions of yourself out there, living slightly different versions of your life? And if their lives are different, maybe that version of you took a different job or never met a certain person. Does that make them a separate person altogether? Or are they still you, just expressed slightly differently? Suddenly, the infinity of space feels a lot less abstract and a lot more personal. This brings us to the fascinating connection between the concept of infinity and theories like the multiverse. While these are often treated as separate ideas, they overlap in intriguing ways. Many multiverse theories, like the one that arises from quantum mechanics, explore parallel realities branching off with every choice or event. But an infinite universe is simpler. Instead of separate dimensions, it implies that all possibilities could simply exist in the same physical reality, separated by unimaginable distances. In other words, the multiverse, and all its strange branching realities, might not be other universes at all. It could all just be happening somewhere far beyond the edge of what we can see. Of course, there's a limit to how much of this we can confirm or even study. Even if the universe is infinite, the portion we'll ever be able to observe or measure is finite, thanks to that cosmic horizon we talked about earlier. The regions of space far beyond our reach, where these supposed duplicates or cosmic echoes might exist, are so far away that their signals, their light, will never reach us. As infinite as the universe might be, we're bound by the limits of localized observation. It's like standing on a small island in the middle of an endless ocean. Even if you know there's no shore in sight, you can only directly experience the little plot of land beneath your feet. It's worth noting that while infinity forces us to confront some strange and unsettling possibilities,
It's also a deeply humbling concept. It suggests that we're not the center of the cosmos, not by a long shot. The idea of multiple versions of Earth, let alone multiple versions of you, might feel disorienting at first, but it's also a reminder of how mysterious and vast the universe truly is. We often yearn to feel special or unique, but in an infinite cosmos, what becomes special isn't individuality. It's the fact that we're here at all, existing in this vast possibility space. Infinity shifts the focus from being one of a kind to being a part of something endless. And that doesn't make existence any less meaningful. If anything, it adds to the wonder. After all, the existence of infinite possibilities doesn't erase what's happening here and now. To some extent, it's a comforting thought, because even if the universe holds other versions of us, or even other versions of Earth, this version, the one we're experiencing right now, is still uniquely ours. Infinity helps us reframe what we understand about the universe, but it also leaves us with profound cosmic mysteries. What if the universe really does go on forever? Where do we fit into that, and how do we reconcile the idea of infinite repetition with the uniqueness we feel in our own lives? Infinity challenges not just the boundaries of space, but the boundaries of our thinking. It reshapes not just how we see the universe, but how we see ourselves within it. And this brings us to a final question, not about what infinity might mean in theory, but about how the universe itself provides the clues. Is the universe infinite, or is it simply vast? Hidden in the oldest light, the cosmic microwave background, are hints about the true size of the cosmos. These whispers from the dawn of time might tell us whether the universe stretches endlessly or loops back on itself. Let's explore what these distant echoes reveal.
What the oldest light in the universe tells us about space.
If you point your telescope to the sky, beyond all the stars and galaxies, you'll find something remarkable. A faint glow, evenly spread in every direction. It's not light from a distant star or even a nearby galaxy. It's older, stranger, and much quieter than that. This light, called the cosmic microwave background, or CMB for short, is the oldest thing we've ever observed. Scientists sometimes call it a whisper from the very early universe. And in that whisper are secrets about the cosmos' past, present, and even its shape and size. Let's rewind to about 13.8 billion years ago, shortly after the Big Bang. Back then, the universe was nothing like what we know now. It was hot, dense, and filled with a glowing plasma, a soup of charged particles, like protons and electrons, swirling and crashing into each other. Photons, or particles of light, couldn't travel very far without hitting something. So the universe was effectively opaque, like a dense fog. But then, something extraordinary happened. Around 380,000 years after the Big Bang, temperatures dropped low enough for protons and electrons to combine into neutral hydrogen atoms. This moment, known as recombination, was when the fog cleared and the photons, finally freed, began their journey. That ancient light is what we now see as the CMB. Of course, the CMB didn't always look like it does now. When it was released, it wasn't the faint microwave glow we measure today. It was a blast of ultraviolet light. But as the universe expanded over billions of years, it stretched that light, shifting its wavelength into the microwave spectrum. What was once a high-energy glow is now a gentle hum, traveling through space, passing freely through galaxies, stars, and even us. We've been floating in this quiet afterglow of the Big Bang our entire lives. We just didn't know it was there until we learned where and how to look. This faint light is immensely valuable to scientists. By studying it closely, they've been able to piece together an astonishing amount of information about the universe's early history. Several missions, including COBE, DUMAP, and most recently, the Planck satellite, have painstakingly mapped the CMB in incredible detail. At first glance, the CMB looks remarkably uniform, with the same temperature no matter where you point your telescope. But under closer inspection, scientists found tiny differences, tiny fluctuations in temperature, varying by mere millionths of a degree. These might seem like insignificant imperfections, but they're anything but.